Hi guys, this lecture is meant to go with homework 10-6. Some of it you actually might choose to skip over, and I'll let you know at what points you guys can kind of fast forward the video or maybe go and reference the worked out lecture key instead. So just kind of keep that in mind. But we're starting to look at all of the different conic sections that we talked about in the last couple of weeks in a different way. So we're looking at today focusing on a parabola and finding a different way to represent the equation using actually concepts that hopefully you guys saw in Algebra 2. So let's take a look at parabolas. The geometric definition of a parabola, a little bit different than how we've been looking at parabolas in vertex form. But here's how we define a parabola geometrically. It's the locus of points. Locus of points means a set of points equidistant from a given line that we call the directrix and a given point we call the focus point or the focus. So in this case, this is the directrix. Don't confuse that with the x-axis. And then the focal point is here. And then the vertex of our parabola is always going to lie between that focal point and the directrix. So here our vertex is there. Now, I've got a way to kind of represent this with an animation. So let's take a look. Okay, so it's a set of all points that are equidistant from the directrix and the focus. Let's take a look at the animation. So it looks like this. Keep in mind, if we're equidistant from that focal point and the directrix, that's what those lines being drawn out to each point represent. All right, so let's watch this again. We've got the directrix and the focal point, and we're drawing all of those points equidistant from that focal point and the directrix. That set of points then that are being drawn, that's what make up that whole parabola. So that is the geometric definition of a parabola. We're going to use that today. All right, so we want to talk about this definition of a parabola. The first thing I'm going to do, though, is kind of actually work through a proof on how we get to that equation. If you'd like to skip this part, you don't have to know how we derive it. You just have to be familiar with the equation. You can go ahead and fast forward to the next slide. All right, if you want to see the proof, let's define what we've got on this graph. So I am going to say this. We've got the focal point here, and we'll call that 0p. Okay, and from the vertex, always in a parabola, right? P is the distance then from the vertex to that focal point. That also means that the directrix is p units away from the vertex as well. Okay, we are told, let's pick a point on this parabola. The distance between that focal point and a point on our parabola is going to be the same as the distance from that point to the directrix. If we're following the geometric definition of a parabola, the distance from any point on a parabola to the focal point is equal to the distance from that same point to the directrix. So we are proving that distance 1 is equal to distance 2. All right, how are we going to do that? Well, I am going to use the distance formula here. I'm going to call this point that we picked on the parabola xy. And I know that the directrix has the equation y is equal to negative p. If our vertex is sitting at 0, 0, we know we go p up to get to the focal point, and we go p down to get to the directrix. That makes this point x negative p. Okay, so let's plug these things into the distance formula, and let's see what we get. Now, distance 1 from the focal point to the point on the parabola is going to look like this. Remember, the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. All right, so here we go. On the left-hand side, we've got the square root of x minus 0 squared plus y minus p squared. That was distance 1. That is equal to the square root of x minus x squared plus negative p minus y squared. That represents distance 2. Okay, what happens when I clean things up? We've got x squared plus y minus p squared, the square root of all of that. That is equal to x minus x is 0. And I can factor a negative out of all of that. That becomes y plus p squared. And then what are we going to do? Let's square both sides. If I square both sides of this equation, I've got x squared plus quantity y minus p squared is equal to y plus p squared. And then I'm going to FOIL. Okay. This is x squared plus y squared minus 2yp plus p squared. This is equal to y squared plus 2yp plus p squared. Okay, what happens? Well, the p squareds cancel, the y squareds cancel, and we are left with x squared is equal to 4py. All right, guess what? That becomes the equation of a parabola following the geometric definition. So on the next slide, that's where we're going to start writing things out. Okay, so the equation, the new equation for our parabolas, which is what you guys are going to use in homework 10-6, looks like this. What we just defined on that last slide. X squared is equal to 4py, where p is the distance from the focal point to the vertex or from the vertex to the directrix. Now, one thing I need you guys to note, that is an upward facing parabola with a vertex at 0, 0. So what happens when we have parabolas facing different directions and the vertex is shifted? So the equations we're actually going to be referring to look more like this, all right? So when the vertex is moved, we have x minus h squared is equal to 4p times y minus k. That is for an up or downward facing parabola. The other equation then is y minus k squared is equal to 4p x minus h. That is for a right or leftward facing parabola. Right? Y is always squared when our parabola opens left and right. So these are really the equations that we're going to be focusing on, less than the one that I wrote up above. Okay, in a shifted parabola, we're going to stick with the vertex as hk, but in this equation, the red one up there, x squared is equal to 4py, that is when the vertex is 0, 0. The focal point then is 0p. We move p units up to get from the vertex to the focal point. All right? So if the vertex is at 0, 0, we move up p. That gives us 0p as the focal point. Directrix is always going to carry the equation of a horizontal or a vertical line. In this case, from the vertex, we go down p units. That gives us the equation y is equal to negative p. It's that horizontal line. And then there's a typo here. This should be latus rectum, not recturn. Last set of points, the latus rectum. I'm going to talk about that in a minute. That is 2p, comma p, and negative 2p, comma p. So let's draw those into the picture and then talk about what the latus rectum are. Okay, so the latus rectum, they are 2 points that connect with the focal point. So they're going to run through the focal point, and they're going to run, in the case of a parabola, parallel to the directrix. So 2 points on our curve that go through the focal point that are parallel to the directrix, these 2 points are the latus rectum points. We define the latus rectum points. We're going to do that on the next slide. But what we want to know about those latus rectum points is that they are always 2p distance away from the focal point. So we're going to go left and right 2p, and then we're going to go up p units to get to those points. Okay, what are the latus rectum? It's the line segment through a focus of a conic section perpendicular to the major axis, which has both endpoints on the curve. So in this case, specifically with the parabola, go through the focal point, run parallel to the directrix. That is the latus rectum, that line segment. In a parabola, the length of that latus rectum is 4p in total. Remember, 2p to the left and 2p to the right of the focal point. Where are they used? Okay, so the latus rectum and eccentricity, which we'll talk about later on in this unit, They can be used when we describe the planetary motion of Newtonian conics. They can be used in celestial mechanics. The latus rectum of a circle is actually the diameter. So if we think about, right, that center of the circle, which is the focal point of the circle, if we go directly through that, that becomes the diameter of our circle. And then we aren't going to get to this year, but when or if we were to do conics in polar, the equation of a conic section in polar includes the value of the semi-lattice rectum, so half the lattice rectum length. Okay, here's where we're going to start the examples that you guys are going to use to do your homework. So first type of example is going to apply for 12 through 18 evens. You guys are going to identify the vertex, the focus, and the directrix, and then we want to write the equation for the graphs that we see in the new form. So in the form that we just discussed in the last set of lecture notes. Okay, so let's take a look at example A here. Well, I can easily identify the vertex. The vertex is labeled already for us, 0, 0. The focal point we'll come back to when we actually look at the equation. So we want all of this information, but let's talk about the equation of this parabola. Okay, this is an upward facing parabola whose vertex is at 0, 0. That means the equation is going to carry this form. X squared is equal to 4py. So let's fill in what we know. I know we've got a point here on the parabola that is 3, 3. I'm going to plug in 3 and 3 for x and y into this equation to solve for p. So 3 squared is equal to 4 times p, which we don't know we're solving for, times 3, which is y. 9 is equal to 12p. Then p is going to equal 9 over 12, which simplifies to 3/4. Okay, so the equation then of this parabola is x squared is equal to 4p, which is 3/4 y. So x squared is equal to 3y is the final equation for this parabola. Okay, if I know p is 3/4, I know that we are going to then go up 3/4 to get to the focal point. Remember, we always go up p for the vertex. The focal point will always sit on the inside of a parabola. That's something that's really important to note there. I know I'm going up to get to that focal point because the parabola is facing up. Now we're going to move p units to get to that focal point. So the focus is going to be 0 and then up 3/4. Last thing, that directrix, if we moved up 3/4 to get to the focal point, we're going to be moving down 3/4 to get to the directrix. As we see, I just graphed that. That's going to be that horizontal line, y is equal to negative 3/4. All right, second example, we want to find the same set of information. So we are given the vertex, that is 1, 1. And then we're going to use the equation to find that focus and directrix. Okay. This is a parabola facing to the left, and it is shifted. It doesn't have a vertex of 0, 0, which means we are using this standard equation. Y minus k squared is equal to 4p x minus h. I know we're using y minus k squared because it opens to the left. If it opened to the right, we'd use that same equation. Up and down would be when x is squared. Okay, we're going to figure out by plugging in information that we've got, what the value of p is. So I know the vertex is 1, 1. Those are going to be my h and k values. And then we've got this other point sitting on our parabola, -1, -3. That's what I'm going to plug in for x and y. So what this looks like when I plug in those values, y is -3, and then -1 squared. And then that is equal to 4p. Now x here is -1, and then h is 1. So let's simplify and solve for p. -3 minus 1 is -4 squared is just 16. And then we get -8p on the right-hand side. Divide by -8, p is equal to -2. All right, p is equal to -2. I can then fill in what I need to write the final equation. Final equation, y minus 1 squared is equal to 4p times x minus h, which is 1. Simplify that, y minus 1 squared is equal to -8 times x minus 1. That is our equation. Now let's take a look at that focus and directrix. Now, because our parabola opens up to the left, I know that the focal point is going to move to the left. So from the vertex, we're going to go p units to the left. Now, p here is -2, but we're talking about distance. So I'm just going to go p units to the left to get to that focal point. That focal point then becomes the point -1, 1. All right, and then if I moved to the left to get to the focal point, I'm going to go right p units, so right 2 in order to get to the directrix this time. That is a vertical line. That is the equation x is equal to 3. All right, so first set of homework is going to be like these two examples.